To connect graphing with first and second derivatives. The first example we will take is f of x equals 3x squared minus 5x minus 2. Yes, it is a quadratic function, and I'm sure you all could sketch that easily without the need of calculus. But we're going to use calculus to show that what your expectation of this quadratic function are going to be met, and we're going to provide the calculus evidence to support that. So in every sketching exercise or graphing exercise always begins by finding the domain. In this exercise, the domain is simply x belongs to R. In others, in rational functions, you might find there's vertical asymptotes or restrictions in other functions that you have to accommodate in the domain. Second, find the end behavior. In this function, again, we know that as x goes to negative infinity, the y goes to positive infinity, and as x goes to positive infinity, y goes to positive infinity. So there's no limit really at the extremes. But if there was a rational function, you might have a horizontal asymptote or a oblique asymptote, etc. And those would be accounted for by the end behavior. Third, find the x and y intercepts. In this case, I could use a factoring approach or a quadratic formula to determine the two x-intercepts or roots, and there x equals negative 1 over 3 or x equals 2. As for the y-intercept, simply plug in x equals 0 in the quadratic equation here, and you get y equals negative 2 as your y-intercept. Now, the difference between regular grade 10 approach and this calculus approach is that we're going to determine the turning point, in other words, towards the vertex. So in step 4, determine the first derivative of f of x, which we call f prime of x. So this is a power rule derivative. You get 6x minus 5. Now 6x minus 5, wherever that equation is equal to 0, that is the location of a possible turning point. Now we know that there is a definite turning point at x equals 5 over 6. If we do 6x minus 5 equals 0, x is 5 over 6. There's definitely a turning point. We know it because we know a quadratic function, what a parabola looks like. But in order to provide more calculus evidence, again, we're not learning it for the quadratic, we're learning this so we could apply it to higher order functions. We draw a number line which shows the sign of f prime of x, whatever f prime of x is. And below that, we see what's the impact on f of x as a function. Now on f prime of x number line, we have the root that makes f prime of x 0, which is 5 over 6. And since f prime of x is a linear function, 6x minus 5, then we know that with a positive slope, this line will have negative y values before the root and positive y values after the root. And as a result, we'll have the sign of f prime of x negative before the root, positive after the root. As you see, if the slope of the tangent is negative, the function would be decreasing, and here the slope of the function of the tangent, is positive, then the function is increasing. You can tell from there that there is a local min at x equals 5 over 6. And the point at that x value, if we find it in decimal and substitute that 5 over 6 value in the x in f of x, we will get negative 4.083 as the y value. And here that would be the coordinates of the vertex x and y. Now also we could tell where the function is increasing or decreasing from that number line. So f of x is increasing where we see that arrow going up, and that is x is greater than 5 over 6, and f of x is decreasing for x is less than negative 5 over 6. The fifth step is to determine concavity, and that takes place by finding f double prime of x. Now if we take f prime of x and we find the derivative of 6x minus 5, technically you're asking what's the slope of that line, which is 6, even if you don't know power rules. So f double prime of x is 6, which means it's always positive in this case. Positive 6 is a positive value. So f double prime of x does not have roots that can alter the concavity. There's only one concavity in this function. And since the f double prime is always positive, therefore the concavity is always up. Now, that we could state as f of x is concave up for all x belongs to R, and f of x is never concave down. Once you get to sketching, I would put the intercepts at negative third and at 2. We have the vertex at 0.833 and negative 4.083. We know that based on the number line of f prime of x, it's decreasing, then the local min, then increasing. So it should decrease towards the local min, then increase. And that would be the sketch for a simple quadratic function. Next, we'll do a cubic function and see a bit of differences, but again, same steps, 5 steps are needed. In this exercise, we know that it's a cubic function, degree 3, an odd degree. The function should start from quadrant 3, end in quadrant 1. We know that the leading coefficient is positive, and therefore no vertical reflection. Again, domain, x belongs to set R, there's no restriction on that, and behavior, it's a bit different from a quadratic function because as x goes to negative infinity, y goes to negative infinity, and as x goes to positive infinity, y goes to positive infinity. So the limit of f of x as x goes to positive infinity is positive infinity. The limit of f of x as x goes to negative infinity is negative infinity. We determine the x-intercept and the y-intercept. To find the x-intercepts, you set f of x equal to 0, and I used the factor theorem here to determine that x equals minus 1 is a root, and then do the long division by x plus 1, which is the factor, to find the quotient, which would be quadratic in this case. And when you factor that, or when you do the quadratic formula, you would get those two additional roots. So the y-intercept, to find it, you set x equal to 0 and you end up with negative 4. Again, steps 4 and 5 are about f prime and f double prime. We need to determine intervals of increase and decrease so we could tell where are the turning points. Derive f of x and simply multiply 3 by 3 is 9, x power, drop the exponent by 1, 2. So 9x squared plus similarly 10x minus 2. So as you see, the first derivative is a quadratic function itself, and if you use the quadratic formula, you'll find the two roots are negative 1.284 and 0.173 if you set f prime equal to 0. Now again, we're going to find the number line showing the sign of f prime of x. This is a quadratic function. We have two roots, so there must be, it opens upwards as well, sorry, so there must be intervals that are positive, intervals that are negative, and the shape we have here would be helping us most determine what are the signs on the number line. So since it's a quadratic equation, opening up has two roots, it should look as such. Look at the function, where is it positive, negative, positive. So on that number line, when you state the roots of the f prime of x, we know that it's going to start positive, change to negative, then to positive. We know these also are single roots, so the signs must change. And as a result, what we see is f of x is going to be increasing since the slopes are positive of the tangents. Here is going to be a decrease on f of x, the slopes of the tangents are negative. And here an increase on f of x, the slopes of the tangents are positive. Those would be the y values at x equal negative 1.284 and 0.173. We sub them in f of x. And you could tell f of x is increasing, x is less than negative 1.284, or x is greater than 0.173, whereas f of x is decreasing between negative 1.284 and 0.173. The fifth step, which is the second derivative, you take the first derivative, 9x squared plus 10x minus 2, and derive it by power rules. You get 18x plus 10. If you set it equal to 0 to determine possible inflection points, you'll see that this is a linear function. There will be a root, and x equals negative 5 over 9. If you subtract 10, divide by 18, and simplify, you get negative 5 over 9. And since this is a linear function, positive slope, positive 18, it's going to look like that here, and the root is negative 5 over 9. Notice before the root the function is negative, f double prime of x is negative. After the root, f double prime of x is positive. So concavity for f of x is going to be down for x less than negative 5 over 9 and up for x is greater than 5 over 9. And that's what we've written here. F of x is concave up for x is greater than negative 5 over 9. F of x is concave down if x is less than negative 5 over 9. Finally, to put the sketch, I would put all the points, the x-intercepts first, the y-intercept. I'd put the turning points. We have a max at negative 1.284, 0.46. We have a min at 0.173, negative 4.18. We know the function is increasing towards the max, decreasing between max and min, increasing after the max. We know the inflection point is at negative 5 over 9 or negative 0.556, negative 1.89 as well. So we know that concavity is down before negative 5 over 9 and up after negative 5 over 9, which we have seen here in the bottom of this page. And that would be the sketch of the cubic function. And as we've anticipated in the beginning, if you remember, we've anticipated the shape to look as such. We just needed to have more accuracy in terms of the turning points, inflection point, and the intercepts. And that would be it for today. Until next time, have a good evening.